So thank you, Sumati, for that brief introduction. I appreciate. Uh, so let me start by thanking the QMAT organizers, Satyabrata, Brijesh, Pinto, and all other organizers, etc. I think it's the first time that I am seeing the whole community, not in even or odd parity years basically together.
Not
and parallel.
Not the whole community, part of the community.
Almost significant part of the community, okay, with correction. Okay, so I'm very happy to see that, and very happy to be here at 9 a.m., which is our typical time for PHY 112 lectures in halls like this for 100 and 200, 350 sort of students basically, which is what we would have had if this hall was full. Okay, so let's start with the talk. I'm going to talk briefly about nonlinear charge and spin transport, and I'll give you a very biased review of literature filled with my own works. Okay, since I get to choose, I'll be extremely biased. Okay, I'll talk mostly about nonlinear charge transport and very little about spin transport, etc. And the main idea that I want to convey to you is the following: that nonlinear charge transport or nonlinear transport in general is a sensitive probe of band geometry and topology of block wave functions, properties, crystalline symmetries, and disorder effects, let's say, etc. Okay. And we'll go through them systematically. As usual, most of the work is done by many of the bright PhD students. Harsh particularly will feature a lot. Harsh is here, he's also in the audience, and the professors or the guides get to tell the story basically. Okay. So keep that in mind. Okay. So this is the broad picture, generalized idea of charges, transport, let's say. So there are some generalized forces which can come from external perturbations, electric field, magnetic field, temperature gradient, strain fields, time dependent or time independent fields, etc. They interact with some quantum material, and they will give rise to transport of different degrees of freedom, transport of charge, transport of heat, thermoelectric transport, spin currents, other degrees of freedom, Valley, orbital degree of freedom, etc. And these we can use to make devices or do diagnostics of properties of materials basically. Okay. So the image is special. It features a recent cover page image by PRL by Avik. Okay. So I thought I'll use that happily. Okay. So what is nonlinear charge transport? Typically for any quantity I'll calculate let's say the current. Okay. The current, and if it is perturbative current, meaning I can expand it systematically in orders of the applied perturbation, then I get a first order response, linear response, which gives you the Dubé conductivity for charge response, for example. What is responsible for all of this lighting in this room, all of our electrical circuits, right? More exotic version of that is anomalous Hall effect. Without any magnetic field, magnetic system can show finite transverse voltage generation on application of a electric field, etc. Okay. That is anomalous Hall effect in linear response. More recently, a lot of work on chiral anomalies in wild semi-metals. Sumati gave a talk on wild semi-metals. Other talks also were there on wild semi-metals. Planar Hall effect, a lot of magneto transport effects, etc. in the linear response regime. And then two orders of electric field, that's the second order response tensor. So there is a second rank tensor, there is a third rank tensor, third order it will become a fourth rank tensor, and so on and so forth. Okay. So the second rank tensor can give you nonlinear longitudinal transport, what is called nonlinear anomalous Hall effect, that we'll discuss in detail. Both of these we will discuss in detail today. Nonlinear transport of other degrees of freedom, spin, Valley, and their thermoelectric counterparts. So this is the broad picture basically, and I'll mostly focus on nonlinear charge transport for most of this talk. Okay. So with that, what is happening? So there are these block quasi-particles, electrons basically, fermionic quasi-particles in crystalline lattices, or bosonic quasi-particles in crystalline lattices, etc., which do translation or rotation, and they have a finite width of these wave packets basically. Okay. So finite width and their motion across this in crystalline lattices reflects in their wave function, which can be used to construct band geometric quantities, specifically Berry connection, Berry curvature, orbital magnetic moment, quantum metric, higher order tensors of band geometric quantities, etc. And these are intrinsic properties of the block wave function, either bosonic or fermionic, electronic quasiparticles, magnons, etc., phonons, etc. Okay? And these band geometric quantities coupled to external perturbations, electric field, temperature gradient, magnetic field in interesting ways, and give rise to new phenomena in transport and optical experiments. So, a lot of what we have known also can be interpreted in this new language, or lot of new phenomena is being discovered, which is captured by this kind of a framework. So, that is the broad idea. Okay? And of course, experimentally there are other tricks, but from a theoretical perspective, we can do three kinds of theory systematically for this. One is Boltzmann transport theory, something that we use in Ashcroft-Mermin to derive Drude conductivity, let us say for example, right. Slightly more generalized version of that is a density matrix picture, which makes the multi-band nature of all of these band geometric quantities explicit, and use them to derive and interpret experimental phenomena. So, that is the broad idea of this talk. Okay. Okay. So, how do I calculate charge transport, let us say, right. So, there is a velocity which is like a current operator, let us say, etc. Okay. I will sum over all possible states. We are in relatively clean systems, so Bloch theorem is still valid. Wherever Drude conductivity works, basically those are the systems that we will mostly talk about. Okay. And there will be a distribution function, which is the occupation probability of a Bloch state, which gets modified by external perturbations basically. So, I take the product of both of these and sum over these, that gives me the current. So, this is like NEV, number of electrons into velocity into charge basically, right. Charge is missing because it is a particle current, but I can add charge and so on and so forth. Okay. So, to calculate this, I need to have information about the intrinsic dynamics of the system, which is captured by the velocity operator, let us say, or velocity expectation value of the velocity, and I should have the impact of external perturbations on the distribution function. Okay. Okay. So, let us go through one by one. So, if there is only, if it was a single band picture, then we know that the r dot or the velocity of Bloch quasiparticles is just given by the band velocity. So, Vk is just the derivative of energy with respect to whatever direction, momentum direction we want to move in, etc. But if you include this multi-band effects and interband coherence effects, etc., a lot of new terms start appearing. Specifically, we have this anomalous velocity terms, which is E cross omega, and this is fairly well known for a long time. Gives rise to anomalous Hall effect, Valley Hall effect, phenomena like spin Hall effect, and so on and so forth. Okay. Another more interesting term is here, which appears only in the presence of magnetic field. This is called chiral magnetic velocity, and this is the reason behind whole of chiral anomaly. Let us say V dot omega, if I transfer the derivative over omega, or if I write it with the Fermi function integral, then you can show that this maps to the while charge basically. Okay. So, this is what gives rise to chiral magnetic effect, chiral anomaly in while semimetals, etc. In other 2D materials also, this term by itself may vanish, but it can combine with other terms, etc., to give rise to interesting magnetotransport effects, negative MR, planar Hall effect, and so on and so forth. Okay. So, that is the r dot dynamics. The position of the center of the wave packet is this is how it moves basically. Okay. Then, how does its momentum change? How does its Bloch momentum change? So, of course, we have Lorentz force, and then we have this additional force, which for the lack of a better name, I just call it Berry force, let us say, etc. Okay. So, just to refer to it easily, and this can combine to give you a lot of interesting effects, magnetoelectric coupling, negative MR. This can give rise to a lot of negative MR, which people interpret in experimental papers as chiral anomaly induced negative MR, even though the material is not wild side metal, etc., and so on and so forth. Okay. So, this gives a lot of chiral anomaly like physics, because this E and B, so coplanar E and B give rise to a lot of interesting phenomena. Okay. And decay is this factor, which is a magnetic field correction, which appears in presence of both Berry curvature and magnetic field actually. Okay. So, the omega is the more interesting thing, is called the Berry curvature. This comes from band properties, the wave functions properties of the whatever quasi-particles we are looking at, magnons, bosons, or electronic quasi-particles, etc. But the main point is that the band geometric quantities omega, particularly in this equation of motion, modifies these equations of motions of wave packets in crystals, and this induces novel transport effects. Okay? And this is a simplified picture. I am talking of only DC perturbations, let's say. If there are AC perturbations, then even these equations get modified. I get other band geometric quantities, etc. Okay? But this already captures a lot of transport effects that we see in the linear response regime. Okay? So that's the idea. So that was the dynamics, the velocities. Okay? How do we see the change in the distribution function? So a lot of other ways to calculate, but one systematic way to calculate this is using this Boltzmann equation, let's say. So G denotes the non-equilibrium distribution function. In equilibrium, this is, let's say, either the Fermi-Dirac or the Bose-Einstein distribution function for fermions or magnons. And so I have regular dynamics in the phase space of the distribution function. So this should be G. And on the right hand side is this dynamics is interrupted by collisions, basically, right? So how do you include these collisions? And one systematic way, quantum mechanical way to include these collisions is through this kind of a integral where W captures the rate of transition from one K state to a K prime state, let's say. And you start from an occupied state and subtract all the outgoing transitions to all the incoming transitions, etc. And this gives you for a specific K what is the total collision integral, etc. So the scattering has interesting elements. So generally, whatever we see in Ashcroft-Mermin and we use to model phenomena is what is called symmetric scattering. Symmetric scattering is where K goes to K prime, scattering rate, and the reverse, K prime goes to K are equal. Okay. And this is what will happen in most of the metals, Ashcroft-Mermin or typical conventional textbooks. This is all that we will discuss basically. And a common approximation that you can make to just make calculations easier is what is called relaxation time approximation, where this I call we approximate by the change in the distribution function from its equilibrium value divided by the time over which it relaxes, right? If you just put it in that equation and solve just the time dependent part, you can show that the non-equilibrium distribution function exponentially relaxes to the equilibrium value basically. Okay? So that's the idea. And you can make it more complicated versions of this by making tau, momentum, energy or frequency dependent, etc. And doesn't change the physics quantitatively. Okay? Qualitatively, doesn't change the physics qualitatively. Okay? So quantitative numbers might change, etc. The integrals become slightly more complicated. But the more interesting thing is asymmetric scattering, which can arise either in time reversal symmetry broken systems, intrinsically time reversal symmetry broken systems, or systems which break inversion symmetry. Okay. So the rate of going from K to K prime and the rate of going from K prime to K are not equal. And this gives rise to phenomena which are called side jump and skew scattering, etc. And these have been discussed at length in the context of anomalous Hall effect from 50s to even recently a lot of work in 2010 to 2020, 25, etc. Okay? And this will become important in the context of nonlinear second order responses also. So just wanted to give you a big picture. Okay? So here's combining everything. So we have this equation of motions which we just saw. R dot, the center of wave packet position, velocity being modified by these band geometric quantities. All of this is in the DC limit. The momentum, rate change of crystalline momentum being modified by this Lorentz force and Berry force, let's say, etc. And we get this phase space volume change in presence of magnetic field. Now, let's say the dynamics, the dr and the dk are not, the phase space volume is not uniform. It also evolves with time. To include that time evolution, you need to change the phase space volume by this decay inverse factor. Okay. So this captures the integral measure R dot, and the G we can do a perturbative expansion, or we can solve that collision integral exactly. Okay. So if we are in the perturbative regime, and most of the experiments that we do are in the perturbative regime because we are seeing Dudet or linear response conductivities basically. Okay. Then we can do a systematic expansion of the collision integral. The self-consistent equation on the right hand side we put equilibrium distribution function and we do order by order expansion basically. So if you do, you will get expressions like this. This is the full expression for electric perturbation and temperature gradient, And this term includes Lorentz force effects, which are too lengthy to write in a simplified manner here, etc. Okay? So this is one way within the Boltzmann transport framework how you calculate conductivity, etc. This is from a calculational perspective. And how do we get this band geometric quantities, Berry curvature, etc., let's say, right? So one simple way to think of Berry curvature appearing is I have a wave function and I get perturbative corrections to the wave function, etc. This perturbative correction you can write in terms of what is called Berry connection. And then products of these corrections when you add, you get Berry curvature, etc. That is one way. This is another very nice way of think about band geometric quantities, which is if I take a wave function in k space and displace it slightly and try to take its overlap, no? How much has the distance changed by changing the k to dk, let's say, etc. Okay? And if I do a systematic expansion, I start getting terms like this basically. Okay? Derivative of the wave function, products of derivatives of the wave function. And this quantity you can map to a symmetric part which is called quantum metric and an anti-symmetric part which is called a Berry curvature. Okay? Simplified this in terms of single band notation, but this is easily generalized to multi-band notation and so on and so forth. Okay? That's the broad picture. So this is just for spatial translation. Likewise, you can use other operators here to derive spin-dependent band geometric quantities and so on and so forth. Okay? And all of these feature in spin transport, orbital transport and so on. Okay? And again, the same idea that this Berry curvature quantum metric gives rise to interesting transport and optical phenomena. Anomalous Hall effect, Valley Hall effect, second order BCD induced anomalous Hall effect, and all of this we will discuss. Okay? And this has been mathematically known for a long time, early 80s, etc. But a more recent review article which presents this in a really nice way is this article by Ashwin et al. Where they discuss this in the context of third order optical responses basically. Okay? And this derives a lot of these band geometric tenses and even higher order generalizations of them. Okay. So let's come to a specific problem. So this was a broad overview, specific problem. So I have linear second order, third order responses we can have. In case we do not have an anomalous Hall, let's say, I have a time reversal symmetric material, a material which does not intrinsically have any magnetism, either ferro or anti-ferro, either kind basically. Okay. Then what is the dominant transverse response in the system? Okay. So if you ask this question, then first order is not allowed. Maybe second order we can start having a Hall response. Okay. And that is what we were looking for. And the recent interest in this field originated from this question primarily basically. What is the dominant B is equal to 0 Hall response? And the second question you can ask, is there a possibility of longitudinal response beyond Roudet corrections, let's say, etc. In linear response we do not have, but in second order can we have, for example, right? In linear response there is one interesting example of intrinsic without scattering time transport, which is in graphene, Zitterbewegung. Right? The conductivity is completely independent of scattering time scale. But it is extremely hard to observe because this is precisely at the charge neutrality point, which experimentalists can almost never reach. Okay? So barring that example, there is no known intrinsic response phenomena in linear longitudinal response. Okay? So is there an interesting longitudinal response which can arise intrinsically? So these are the kind of questions we are looking for addressing in this particular talk. Okay? And this field was mostly, so there's been a lot of past works, second harmonic, third harmonic, higher harmonic measurements we have been doing for ages in the context of optics, etc. But recent interest in nonlinear DC transport particularly was initiated by this particular paper by Liang Fu and Inti Soderman. And they showed that the answer to the first question, can we have Hall response in a time reversal symmetric system? And it turns out that second order we can have Hall response even in time reversal symmetric system. And this is induced by what is quantity which is called the Berry curvature dipole. So we had the Berry curvature, we take a momentum derivative of the Berry curvature and thus integrated over the Brillouin zone, that is the Berry curvature dipole, which is this quantity in the blue text. So the dou B is the momentum direction, dou omega by dou k in the specific B direction, let's say, etc. Okay? And it has some scattering factors, etc. There can be a correction of 2 here, which was realized later, but yeah, other than that. Okay? So that's the idea. And what do we need? What we need is inversion symmetry breaking. Okay? And like any dipole response, we need mirror symmetry breaking. So other symmetries need to be broken in the system, but in whatever direction we want, we need definitely inversion broken crystals, and we need mirror symmetry breaking. And the major idea is the following, that I get this anomalous velocity, which is E cross omega, and the distribution function, I can get a linear order correction in electric field, which is also proportional to the scattering time basically, right. So both of these I combine, I get 2 powers of E response, and a response which is also proportional to tau. So that's the second order Hall response. And this paper initiated a lot of interest in this field, etc. And this was one of the first, so there are a couple of papers which came back to back. Just show you one of them from this MIT group by Pablo. So they did it in WT2. So this is WT2, and as usual, so experimentally you apply a finite frequency. These are really low frequency, few megahertz, few hundreds of hertz, let's say, etc. And you measure a lock-in based 2 omega response in the voltage generated. Okay. So you measure, so you apply voltage longitudinal, and you measure across these leads basically, and depending on the gate voltage, which biases the density, you see this quadratic fits basically, which go at different places, etc. Okay. So this is the first, one of the first demonstrations of this nonlinear Hall response in a time reversal symmetric material which doesn't break in, which doesn't have any magnetic field basically. Okay. So that's one of the dominant corrections. And of course, I should be able to have a nonlinear Dubé correction. Nonlinear Dubé corrections typically come from expansion of the distribution function. So if I consider second order expansion of the distribution function, I should get a term which is proportional to tau square basically, right. So that contribution I should always have, and Dubé contribution I should be able to have in longitudinal direction also, and in transverse direction also, right. Though we hardly see transverse version of Dubé Hall effect, symmetric Hall effect, but it should be allowed in some possibility. Okay. So these are the two of the responses, let's say, etc., coming from correction in the distribution function. Next question, can we have some intrinsic responses without any scattering time scale involved? Okay. And this can in principle come from second order contribution to the wave function corrections of the Bloch electrons, etc. Okay. And this was promptly discovered recently, few years back. And one way to understand this easily is we had this anomalous velocity E cross omega, and the wave functions also get corrections in E. So if we include them correctly in omega, then omega gets a correction which is proportional to electric field power, let's say. So I get a corrected version of anomalous velocity, and this is called Berry curvature polarizability Hall effect. It features quantum metric and so on and so forth. Okay. So if you want a detailed expression, then G's are the quantum matrix, and M and P denote the bands, and B and C are the transport directions basically. Okay. This is a full expression, and this is just proportional to the Fermi function. So this is a Fermi C response. So most of the responses we see are Fermi surface responses basically, okay, except for the anomalous Hall in the linear response regime. Okay. So this is a Fermi C response which captures the intrinsic properties of the wave function. Okay. So this was sort of discovered in this particular, so this was already there in 2014 in this paper as a correction to the Berry connection, okay, this term basically, and this induces this particular velocity correction, and it was mapped to a specific Hall effect in these two back-to-back papers in 21 basically. So this BCP induced nonlinear Hall response. This was also experimentally discovered, but before coming to the experimental papers which probe this, what we wanted to ask, motivated by these papers, is this the complete story or are there missing contributions basically? Okay. How do we capture other terms systematically and on the same footing? So generally all that was being done till we asked this question was people would specifically focus on one specific correction, okay, and do calculations only for that specific correction. Okay. So we wanted a unified picture such that if I do one calculations, do I get all of this systematically out of one calculations basically. Okay. Even in a simple relaxation time approximation. And some of this is described in this particular PRB. And so if you think of the full problem, then you have band geometric effects, scattering effects, symmetric scattering and asymmetric scattering, And you can have correlation induced effects beyond the mean field, let's say, etc. Mean field is already included in the band renormalized band geometric quantities, etc. But if you want to include some strong correlation effects, right? So we'll do a simplified calculation. We will ignore asymmetric scattering for now. We'll come back to it later, and we'll completely ignore strong correlation effects, basically. So simpler problem, only band geometric and symmetric scattering effects we will discuss in this particular way. And a nicer way of doing this calculation, instead of focusing on term by term contribution one by one, you can do a unified calculation by this density matrix picture. And the idea is relatively simple, basic quantum mechanics. So I have a velocity operator in the interaction picture, let's say, and I'll just take the trace of that with the density matrix. And all the dynamics, the wave packet dynamics, etc., goes in the dynamics of the density matrix, basically, which I should calculate self-consistently using the fully non-perturbative, the H0, which is the bare Hamiltonian, plus disorder effects or interaction effects, whatever are needed, plus light matter or electric field induced perturbation, basically, in the Hamiltonian. Okay. And you work in the basis states of H0 because that is the only definite quantity that we have. The R operator here is the derivative in the momentum space. So that captures the derivatives of the wave function, which translates to band geometric quantities, etc. And there's some mathematical things you need to take care of, covariant derivatives, etc. We will not worry about that. Okay. So if you do a systematic calculation, then these are the 4 contributions that we found. So this, I already told you, comes from second order in the scattering time scale. Nonlinear anomalous Hall we already had in N.T. Soderman's paper. Nonlinear BCP Hall were predicted in these 2 papers I showed, etc. We found that you can have another contribution which is a different symmetry property, and it can lead to dissipative contributions in both longitudinal direction and Hall, basically. But this is intrinsic. So the response is a Fermi C response and proportional to the Fermi function itself and not its derivative, basically. Okay. So these are the 4 contributions that are there in second order response without including asymmetric scattering as of now. Okay. And so for the anomalous Hall, for example, we use the anomalous Hall response to study a nice problem. In topological materials, probing topological phase transitions is sort of difficult. We are relying on indirect signatures which appear in the resistivity measurements, etc. But they can also arise from metal insulator transitions, for example. Okay. Topological transitions are slightly hard, and Moire materials specifically have this valley churn transitions. So if I change the vertical electric field, I can change the churn number of the bands of the 2 valleys, basically. Okay. And I go from churn number 1 to churn number 2 and so on and so forth. Okay. And we showed in this particular work by Mandar's group primarily that you can use this BCD response to probe this topological phase transitions. Okay. So that's one example of usefulness of where this nonlinear Hall really plays an interesting role, interesting diagnostic role to detect topological phase transitions. Okay. I'll talk more about this. So here's the calculated valley churn diagram for this twisted double bilayer graphy. Okay. So this is in the phase space of delta, which is the vertical electric field, which experimentalists can tune by means of combination of top gate and bottom gate, and strain which you can which is generally there, and what happens. Okay. So you see that as you tune the vertical electric field in any regime, you get this, go through this series of transitions, basically. And here are few of them. And this is just the band gap, so the direct band gap, the point at which they have to touch, etc. And you can show that how this sort of evolves for specific transitions, basically. First conduction band, first valence band, and so on. Okay. All of these transitions are accompanied by band touching points, so this is important. And they are generally different from metal insulator transitions, which are just density of states overlap. So the bands may not touch, but I can still have metal insulator transition. Okay. The bands can cross also completely, and then also I can have metal insulator transition. So these are slightly different, basically. Okay. And this, since it's controlled by the valley churn number, which is also proportional to the Berry curvature, it is not a surprise that the Berry curvature dipole induced nonlinear Hall effect also captures this churn transition change, basically. And it will show up as signatures in some transport measurements, this nonlinear Hall transport measurements, basically. Okay. So here's some what happens to the band structure, distribution of Berry curvature, etc. as you go across the phase transition. So 1 and 2. Okay. And you can measure this. Okay. Now, all my experimentalist friends would be upset that, you are all talking about currents, but we almost never measure current. We measure voltages. Yeah. So, calculation is easy in terms of, applied electric field and calculating currents basically, right. So, we have to map to a right language to come to the experimental viewpoint. Okay. So, you can do some careful scaling analysis of this problem, including all possible contributions. And what we can show is, you have a relation like this, that if you write in a scaled form, getting rid of tau, etc., then the nonlinear Hall voltage divided by the longitudinal Dude conductivity square basically should be proportional to the nonlinear conductivity scaled by the sigma xx basically. Okay. And this is what the experimentalists can do and filter out intrinsic contributions to sigma xx. So, starting from this, you can show by a careful disorder scaling analysis that you have this prefactor. So, these guys are proportional to 8 plus b and sigma xx square, and the a, which gives you the slope, which is a combination of BCD and asymmetric scatterings, etc. But the prefactor b, if you do it at low enough temperature to discard phonon scattering, etc., then the intercept only gives you the Berry curvature dipole induced contribution. So, this is the way to experimentally extract the BCD contribution, and this mapping is very, very important. Otherwise, we are in different worlds basically. Theoreticians are this contribution, that contribution. Experimentalists say I will measure one current basically, right. How do you distinguish between all of these? You give me a recipe. So, this is that recipe. Okay. So, the intercept of the scaled curve, this particular scaled curve gives you the square of the Dude conductivity. And this is not entirely done for nonlinear itself. Similar analysis has been done in 2015, etc., for anomalous Hall, for example. So, this is just taken from that and generalized to this particular problem. Similar analysis has recently been done for third order responses in altered magnets, etc. Okay. Okay. So, here is the experimental data from Mandar's group, and so you have this ratio V2 omega xy signal as a function of displacement field. This does not give you much, though you see some changes at this point, but this can also be induced by metal insulator transition. But if you plot on the scaled VA as a function of sigma xx square basically, then you see this very sharp change in the slope of this, and if you extrapolate, the intercept change completely basically, right. So, this is the signature of topological phase transition. So, the Chern number or the Berry curvature dipole is suddenly changing across the topological phase transition basically. All other thermodynamic quantities have to change in a continuous way basically. Okay. So, that is the idea, and it roughly matches with some playing around with the system parameters with where the phase transitions are expected basically. Okay. So, this is one example where Berry nonlinear Hall predictions were used to decipher topological phase transition. Here are some other examples again from Mandar's group. Same Berry curvature dipole was used to decipher stacking order basically, right. So, AB or ABBA stacking between twisted bilayer graphenes in this particular work. More recently, they managed to do finite frequency strain coupled to the device basically. Okay. And based on the strain, you get harmonics in the frequency of strain for different responses, and these different responses capture different derivatives of the Berry curvature, etc. Okay. So, that was captured in this particular work, and some of these aspects particularly for Moire systems we described in this review article, which is a combination of experiment plus theory and the new phenomena, which was fractional anomalous Hall basically. So, we did a careful review of that in this particular. Okay. So, this is just for okay. So, this is the experimental papers which captured the nonlinear BCP Hall. Okay. So, this quantum metric induced nonlinear transport in topological antiferromagnet. So, both of them were sort of back to back, Nature Science 2023 basically. Okay. And quantum metric nonlinear Hall in a topological antiferromagnetic heterostructure. Because this particular BCP induced Hall, you need to be in a PT symmetric material, and PT symmetric is antiferromagnets which are on a bipartite lattice basically. So, if I just invert, the lattice maps, but the spins do not map. But if I do P and time reversal, I invert, and then the spins also invert because of time reversal symmetry. So, I have this perfect mapping. So, in this particular system, this quantum metric effects play an important role, and Yeah. So this particular paper also features one of my former students who is in SN Bose currently. Okay. So this is nonlinear BCP, and this is the new contribution that we had predicted, nonlinear BCP dissipative. And this is one of the first examples I know of a intrinsic wave function based response in a, so we are 35 or 40? 40, okay. So I'll quickly go. Okay. So it can have both longitudinal and transverse contributions basically. Okay. So this is roughly the full story. I'll jump through the story of asymmetric scattering, let's say. Okay. So that's important. So how does asymmetric scattering affect second order charge transport, let's say, and both Hall and longitudinal? So that's the problem. And as I already said, that the rate of scattering from k to k prime is not equal to k prime to k. So this, if you do, the idea of calculation is we calculate the scattering rate, and in the scattering rate we generally use the for Ashcroft-Marmin, let's say, symmetric scattering, the Bayer wave function and the Bayer wave functions. But I can have higher order contributions in terms of scattering if I take the disorder modified wave functions, etc. And if you take the third order and systematically, then you start getting this antisymmetric part as well. And this gives rise to skew scattering and side jump like processes. The point of this phenomena is you can show that even the side jump mechanism, which is like a discrete jump in the electron position, is proportional to the wave function properties, and this can also be mapped to a Berry curvature in some approximate regime of short range potentials, let's say, etc. Okay. And skew scattering also is given by this kind of a Wilson loop structure for wave function properties, and it can also be mapped to a Berry curvature. So the point of showing this is that even extrinsic responses, even this asymmetric scattering responses are peaked near the band edges, where these band geometric quantities are enhanced. Okay. That's what this captures. This is one paper by ZZ Du et al., which showed that the extrinsic scattering, this asymmetric scattering contributions can be almost as large as intrinsic scattering contributions, in particular in this nonlinear Hall effect basically. Okay. So that's the idea. I was going to show you some results for longitudinal, but I think I'll just summarize. Okay.
I think that was 5 minutes you lost a bit.
Okay, okay, thank you. So this is what happens when you have Sumati as chair. Okay, so I get extra time. Okay, so again, asymmetric scattering induced longitudinal transport, right? So the band geometric Berry curvature always induces transverse transport. It cannot contribute to the longitudinal channel basically. Okay. So can I have scattering induced longitudinal currents basically? So it turns out yes, and can be used to design what is called a diode-like response, which is typically called as non-reciprocal response. So I apply a voltage in the forward direction and I apply a voltage in the backward direction. The currents are different basically. Right? So I can have diode-like physics, let's say, etc. And we showed particularly with Harsh in this particular archive that this nonlinear side jump and nonlinear skew scattering contributions can give rise to this non-reciprocal effect in time reversal symmetric systems also. So the community used to believe, or there was a wide misconception that you need time reversal symmetry breaking for having this non-reciprocal longitudinal responses. Okay. So that's what this addressed, and Harsh did nice calculations to show that bilayer graphene near this lift shift transitions basically. Bilayer graphene has a lot of lift shift transitions near the band edges. Okay, can give rise to as large as 40% non-reciprocity. And it roughly maps to published experimental data, which we had worked for in other paper basically. Okay. So that brings me towards the end. Atin is in the audience, so I could not skip this paper. So again, nonlinear Hall and its manifestations to probe some physical phenomena basically. Okay. So in this particular paper, there are specific band features which are induced by interaction effects. So the van 't Waals singularity splits into two, but how it splits and what is the root is different. And it turns out that this Berry curvature based responses can probe this. They change sign across one, they do not change sign across one. With Atin, there was a physical phase transition, charge density wave phase transition, and the responses change across the transition basically. Okay. So that's what this paper captured. And with Tanveer, who's one of Arindam's student, former Arindam student now in Spain, etc. We probed, if we can, in bilayer graphene-like system, can we probe lift shift transitions basically by means of this Berry curvature dipole physics. Okay? So the whole point of showing this biased review is to highlight the point that theoretically nonlinear response hai, hona bhi chahiye, theek hai, right? But can it be used for a diagnosing or predicting some physical phenomena, which is sort of hard to capture in linear responses, or conductivity may not show, other thermodynamic responses may not show, and transport responses are easy to measure basically, right? Almost most of the institutes in our country will have transport labs basically. Almost all labs would be doing basic transport measurements, etc. Okay, so that brings me towards the end. So I mostly describe charge responses, but then you can keep asking what about nonlinear thermal, thermoelectric spin responses, etc. So here's just one prominent literature from the recent paper where people showed large nonlinear Nernst effect in trilayer graphene arising from again this asymmetric scattering and so on and so forth. Okay. So this field is wide open. Here are some of biased review, our own contributions. So nonlinear thermal transport of fermions, right? Nonlinear thermal transport of bosons. This paper also has Arijit, one of my colleagues who should be in the audience. Nonlinear thermoelectric transport of fermions. So you can have intrinsic nonlinear Seebeck and Nernst effects, for example, which doesn't depend on scattering time scale. Nonlinear spin transport, nonlinear valley transport, nonlinear orbital. So there are a lot of possibilities basically, even in this simple, easy, non-interacting regime, let's say. Okay. So that brings me to the summary. So the broad problem is the following: nonlinear electrical, thermal, and thermoelectric responses, let's say, interplay of band geometry, disorder, and crystalline symmetries. Responses you can calculate across charge, spin, orbital, valley, and other degrees of freedom. And I hope I was able to convey some of my excitement of this field, and make a point that nonlinear transport is a sensitive probe of band geometry and topology of block wave functions, crystalline symmetries, though I didn't discuss crystalline symmetries specifically in this talk, and disorder basically. Okay. So with that, I'd like to say a very loud thank you to the whole of condensed matter community, particularly all of those who see this slide and are here at JNU QMAT. Okay.
Thanks for this very nice talk. And we have time for a few questions.
I start. I read an article by Claudio Shamon some years ago about Berry curvature phenomena, diamond-like material. Amazing, like we take graphene with there is no spin orbit coupling. If you look at the K or K prime point around, there are local, very magnetic fluxes and so on. But in a diamond there are lines and vortices in Berry curvature.
That is possible, yeah.
So I wonder if there are attempts to understand that, because you dope the system and carriers are in some corner. Some of these things that you
yeah. So diamond will have to do an optical probe. Yeah. So there should be orbital magnetic moments definitely, and even Berry curvature possibly, but it has a very large band gap.
But if you dope the system,
yeah. Yeah, if you, so even without doping, you should be able to probe in optical experiments.
But then there are.
Yeah, there are. So there will be a lot of mixed effects, etc. So the major problem, challenge generally is isolating in experiments. This real, what is the origin of what I see, basically, right? Because there are 10 different effects. How do I separate them, right? Yeah. So, but if attempts are made, then definitely, yeah.
What is fascinating is from graphene, there is no spin orbit coupling. Locally, there are some valley there.
Yeah. Locally, there are circulating orbital magnetic moments, which gives valley Hall effect, etc. Right? Yeah. Yeah. So one point I missed, skipped the slide is, so this nonlinear second order conductivity, we used to predict nonlinear valley Hall effect for the first time in a inversion symmetric material. So graphene-like material, let's say. This was a couple of years back, and last year already there are at least a couple of demonstrations. One of my friends here told me that their lab also has some signal. We are yet to talk, but these are things that for students particularly, I used to get excited when I was a student. Some of my professors, let's say, TVR, HRK, Shyam Sastri. So we would hear stories about how they made some prediction, and it was seen in a recent experiment, right? That is what we grew up being excited about. Okay, so I'm happy to contribute a bit to that excitement.
Amit?
Yeah,
Hi.
please.
Yeah. So in that slide, that was just after the quantum kinetic equation, where you summarized the 4 possible contributions, out of which the last one was yours.
Yeah.
You made the comment that there is an intrinsic dissipative response which depends on the Fermi sea instead of Fermi surface.
Right.
How does one understand that? Because it's very counterintuitive. The whole idea of dissipation is it has to be the order of the perturbation you put. That's why one can think of a Fermi surface effect.
No, it is proportional to the electric field. So
No, I understand. But if you apply a small electric field, even if it's second order, how can a dissipative response come from the entire Fermi sea? How would one understand?
Yeah.
Because
So
it's counterintuitive.
Yeah. So dissipative and non-dissipative is a way of symmetric in the field indices or anti-symmetric in the field indices, let's say. Okay? So the dissipative and non-dissipative terminology, the way I use is basically J dot E summed over all, let's say, Einstein summation basically is 0 or non-zero. Okay?
Yeah, but
so this is
you are losing power.
You are losing power.
But then you are losing power from entire Fermi sea by applying a perturbation that is very small.
Yeah.
How is that possible? How is it tau independent?
Yeah. So something else might carry the power basically, right? May not be scattering, etc. So that is not baked into the theory. Within this limited S0 disorder and electric field, right? How it is lost is a good question. I don't have an immediate answer actually. Yeah.
Thank you.
A very wonderful review of your extensive work, Amit.
Mm-hmm.
So my question is in relation to your statement of the emergence of a Hall-like effect, though the magnetic field is 0, but because of the Berry phase effect.
Yeah.
Now, can one physically try to understand this by relating the Berry phase to an Aharonov-Baum-like phase?
Oh, yeah.
where there's a vector potential and
Yeah.
there's a pseudomagnetic.
No, definitely. Yeah. So this is particularly for students. So very interesting question. So how do I think of Berry phase, let's say, etc. Right? So and the connection is Aharonov-Baum phase, right? So what happens? So magnetic field, how did we understand, right? So if I take an electron and move it around a circle in a magnetic flux, I pick up Aharonov-Baum phase basically, right? And then Aharonov-Baum phase is nice to have, but not very physical when I think of dynamics of particles, etc. Right? So then I map it to a gauge field. That gauge field is also abstract and lot of degrees of freedom, so not very useful physically. If I map it to a force, then the curl of that gauge field gives me a magnetic field basically. So very similar idea in quantum dynamics. So this comes from Maxwell's equations, right? Schrodinger equation, different set of equations. Again, I take an electron or particle and go around a circle. I develop an extra phase, which is called the Berry's phase basically, right? Since we are here, Panchratnam phase, let's say, more appropriately. Okay. Again, the same phase I can map to a gauge field. This gauge field is Berry connection. And this Berry connection has a degree of freedom depending on the system choice, etc. I can have many of them, so not very physically useful. Can I map it to a field? So it turns out that the Berry curvature is just the curl of the field. So summary, Berry curvature I can think in terms of magnetic field in momentum space. Okay. Just like magnetic field I think in terms of physical space, and magnetic field makes the electron go around. Berry phase is magnetic field in the momentum space in a hand waving way. It also makes the electron go around. Okay.
And the kernel of that vector potential will give you the effect.
It does. In fact, I had a slide, but I removed it later.
Yeah. Nice talk. So I was wondering with these.
Yeah.
nonlinear coefficients.
Right.
The coefficients involved in the nonlinear electrical response, thermoelectric response. So just like with the linear coefficients, you have things like the Wiedemann-Franz law and
Yeah.
the Mott relation.
Yeah.
Do you have similar relations even for nonlinear coefficients, and which ones? Because you have many more nonlinear
Yeah.
coefficients than linear ones.
Yeah. So the answer to that is it's not universal like in the linear response regime, let's say, right? So nonlinear Dude, for example, will map to thermal conductivity and A. And the mapping just comes because it's just the higher order derivative of the Fermi function. So Sommerfeld expansion, the same thing works with a different coefficient. Okay, but a lot of these responses are not there in the linear response regime. So then there is no mapping. Also, what electrical response shows and what temperature gradient shows can have different contributions. So then there is no one-to-one mapping basically. Okay. So I hope this answers. Yeah. Okay.
Hi, thank you very much for the
Yeah.
nice talk. So since you mentioned the disorder, so I was wondering, for example, in the case of like Vedic curvature, in presence of these disorder systems, we need to rely on these real space kind of formulations, right? Like for example, Bott index, something like that.
Yeah, amorphous systems, let's say. Right?
Amorphous
Yeah.
systems. Right? So is there similar kind of formalism for Vedic curvature dipole itself?
Waiting to be developed.
Oh, okay.
See, for example, there were some works by my colleague Adhip generalizing anomalous Hall or Chern number idea via Bott index to amorphous systems basically, right? So Berry curvature dipole, there might be already papers. BCP induced, there are not, I'm sure. Okay, and extrinsic scattering, etc. How do you do is not clear basically. So waiting to be developed, please. Yeah, Tamagna. So Tamagna was a UG student with me at some long back time scale.
Thanks. Very extensive, very nice, informative review. I have a slightly naive question and a slightly speculative question. I'll start with the speculative question. You said that there will correlation effects. Looking at it is a future problem.
Yeah.
But I'm wondering what kind of correlation effects would be truly non-perturbative and outside the regime of the perturbative extension. For example, nowadays there has been a recent discussion on dynamics in kinetically constrained models in the sense of dimer models, where the dynamics essentially maps to a single particle hopping on the many-body transition graph. So in that case, the hopping is not really on a lattice. And it's on a graph.
Yeah, it's
Does
on
all of your formalism carry over even if you don't have?
Yeah. See, as long as you have done the mapping to a single particle like framework,
Yeah.
either in a real space or in some other hypothetical space, let's say, graph space or whatever,
Yeah.
then the framework works. Mapping it back might be an interpretive problem. Meaning in the graph space, I get a BCD, right?
Yeah, but you don't need momentum?
I can do a real version,
Okay.
amorphous basically, right? Yeah. Amorphous lattices or some other.
Maybe
Yeah.
we stop.
Yeah.
So I'll ask you the naive question, Liz.
Yeah. I'm here. So at T, and I like answering student questions over T, please. Okay. I'm from IIT Kanpur. Come on.
Thank you. I think we are out of time, so let's thank Amit for a wonderful talk.
Thank you so much for sharing this session and being first to the review speaker.
Thank you, Amit. Okay.